Hi guys, welcome back. This is our second week of remote learning. We are continuing with Unit 9. We are on our third day of Unit 9. Today we're going to be learning about equilibrium and Le Chatelier's principle. Um, I'm using uh, the notes from Mr. Allen, I believe his name is. Um, he he was very concise with his information, so I'm using Mr. Allen's notes. Um, Breakdown for the today, what is due is you have a reading with 11 questions based on the text. You have classwork 1, which is 3 practice problems on Le Chatelier's principle. And then you have regions questions, 5 regions questions on test wizard on Le Chatelier's principle. So let's get started. So this is our due now for today. Just to get us a little bit, not the actual questions, but the images. Remember on Friday we left off with potential energy diagrams and excellent endothermic. So by just looking at the graph on number 6, you can tell that this is an endothermic reaction because we are producing more heat towards the end of the reaction, meaning that we gained heat. And then for number 7, this would be an exothermic reaction because we are losing heat towards the end of the reaction, basically. All right. Remember, for our forward reaction, we are going from the reactants to the products. Our reverse reaction, we're going from the products to the reactants. The 3 parts of the potential energy diagram will not change, whether it be for endothermic or exothermic. We have our reactants, our activation energy, which is our hump, and then we have our products, which is on the end. All right, so today we're going to be talking about equilibrium. Now, to get us started, we need to know that equilibrium occurs when the rate of the forward reaction equals the rate of the reverse reaction in a closed system. Closed system meaning that we are not adding anything to the reaction, we are not manipulating it any way, it is occurring on its own. So equilibrium occurs when the rate, and remember when we're talking about rate we mean speed, so technically equilibrium occurs when the speed of the forward reaction equals the speed of the reverse reaction. Now there are 2 different types of chemical equilibrium. We have chemical and physical. So physical equilibrium, it could be an example of phase change or phase equilibrium, meaning the rate of our melting is equal to the rate of our freezing. The speed of our melting is equal to the speed of our freezing, or the speed of our evaporation is equal to the speed of our condensation. We also have solution equilibrium, which occurs at the saturation point, meaning the rate of the dissolving is equal to the rate of crystallization. Think of rock candy as an example. As it's dissolving the sugar, we're also creating sugar crystals. And then we have chemical equilibrium, where the rate of the forward reaction is equal to the rate of the reverse reaction, or the rate of the breaking bonds is equal to the rate of forming bonds. Now, in terms of concentration, we cannot have a chemical reaction without concentration. So concentration will always be constant for the forward and the reverse reaction. It will always be present, but the rate of the forward will always equal the rate of the reverse reaction. There's a couple example problems. I answered this one already. So a chemical reaction is at equilibrium. Compared to the rate of the forward, the rate of the reverse is obviously B, the same, and the reaction continues in both directions. Remember, this is a continuous reaction. We have those double arrows, meaning the reaction is not going to stop until it runs out of material. Now, number 3 says which factor must be equal in a reversible chemical reaction at equilibrium. I'm going to give you time. You can go ahead and solve that one down in the comments. Now, so we have Le Chatelier's principle. Like I said, I took the notes from Mr. Allen because his one was really compact. So basically, Le Chatelier's principle is saying that we have our system is at equilibrium, meaning the rate of our forward equals the rate of our reverse. It's at equilibrium. However, it will respond in the presence of stress. Stress being any changes to temperature, concentration, or pressure. So the same way you react to stress is the same way our chemical reactions react to stress. Meaning you're stressed out, you're going to shift away from the stress, right? The same way, that's the same thing our chemical equations go through. They get stressed out by either temperature, concentration, or pressure. They're going to move away from the stress to relieve it. So we can either shift to the right, that means towards the products, or we can either shift to the left, towards the reactants. So once we have a shift, we are going to cause the concentration of our substances to either increase or decrease based on that shift. So we need to pay attention to that. I'll try to explain it as slowly as possible, but we do have example problems that we can work through. So when it comes to concentration, so when we introduce concentration, it's either being introduced or taken away in a chemical equilibrium. So, for example, if we increase concentration of a substance, we're going to shift away from that increase. So, over here, and I'm going to do this as we move along. So, over here we have this chemical equation. N 4NH3 gas plus 5O2 gas at equilibrium will give us 4NO gas plus 6H2O gas plus heat. So since I see heat on the product side, I can already tell you that this is going to be an exothermic reaction. So we have if we add H2O, H2O is on our product side. So if we add H2O, we're going to shift away from that. So because H2O is on our product side, we're going to go ahead and shift towards our reactants, right? Now, because we shift towards our reactant, anything on the reactant side will increase. And by default, this NO2 is going to look like it decreased. So, the concentration of NH3, remember, if it's written in brackets, it really means talking about concentration. And the concentration of NH3 would increase, right? So I'm going to write an I right here. So if we add O2, now O2 is right here, right? Let me change my pen a little bit. O2 is right there. Here's O2. If we add O2, we're going to shift away from the increase. So we're going to go towards our product side. And because NO2 is where we're shifting towards, the concentration of NO2 is going to go ahead and increase. NO2 would increase, and so would H2O. So everything on this side will go ahead and increase, right? But then anything on this side, which is basically NH3, is going to go ahead and decrease. Just pay attention to the colors. If we add, let's get back over here. If we add H2O right here, we added H2O already, right? We already know the system is going to shift towards our reactant side. But NO2 would go ahead and decrease. Even though technically it's not decreasing, it just, in comparison to the shift, it is decreasing. So if we add NO gas, which is on our product side, which concentration would decrease? Well, that would be H2O, because NO2 increasing will shift towards the reactant side. And anytime we shift towards that side, we are increasing that side. And by default, whatever was on our side looks like it's decreasing. All right. All right, so let's go to the next one. So what happens if the concentration is decreased? Very simple. So if we decrease the concentration, we're going to stay on the side that decreased. We're going to stay on the side that decreased. Why? Because whatever was replaced whatever was taken must be replaced. I'm going to say that again. Whichever side is decreasing, whatever substance is decreasing, we're going to shift back to that side because we must replace what was taken. So oxygen over here is being removed. So the system will shift towards the reactant side because we need to replace what we took away. And then NH3, by default, because now the concentration is focused over here, would go ahead and increase. If we remove water, which is H2O, the system will shift towards the product side because we need to replace what we took. And NO, the concentration of NO would increase because it's benefiting from that shift. If we remove ammonium, which is NH3, then which concentration will decrease? Well, if we remove ammonium, which is NH3, we're going to remain on that side, or we're going to shift back towards the reactant side, meaning the concentration of O2 would increase, and anything that didn't get the shift would decrease. So our concentration of NO and H2O would decrease. If we remove NO gas, which is right here, which concentration would increase? Well, if we remove NO gas right here, which is on our product side, we will shift back towards our product side, meaning that the concentration of H2O would benefit and it would increase as a default. All right. So, temperature. Temperature, remember, if we see temperature or heat or energy or kilojoules on our product side, this is an exothermic reaction. When we see it on our reactant side, it is a endothermic reaction. Same thing with concentration, we're going to do with temperature. Meaning, if we increase temperature or heat, we're going to shift away from it. And wherever we shift, we're going to benefit that side. However, if we decrease temperature, we're going to shift towards the side that contained the heat, and we're going to benefit that side. So, if we add heat, we have this chemical equation right here. If we add heat, which concentration will decrease? Well, if I add heat, I'm going to shift away from it. So I'm going to go this direction. I'm going to go towards my reactant. And I'm going to go ahead and increase anything on my reactant side. So by default, my product side would look like it decreased. So back we have NO and H2O again. Now, because heat shifted to my reactant side, my NH3 and my O2 have gone ahead and they have increased, because by shifting temperature there, I have more collisions, and more collisions means more of my reaction. Now, when it comes to temperature, remember, temperature only affects gas only. So if the chemical reaction does not have a gas, we cannot, and I state this, we cannot conduct a shift. So when we increase pressure, we're going to shift to the side with the least amount of gas molecules, the least number of moles. Just add up all your coefficients on the sides, on your reactant and your product side, to see how much of which one has the least and which one has the greatest. I'm going to say that again. Add up the coefficients on your reactant and your product side to see which one has the least and which one has the greatest. But when we increase pressure, we're going to shift to the side with the least, and with decreased pressure, we're going to shift to the side with the greatest. So, if one side has 9 moles and the other side has 10 moles, when I increase pressure, I'm going to shift to the side with 9. But when I decrease pressure, I'm going to switch to the side with 10. All right. Be right back with the practice.